am Shanawaz. In last lecture we have studied that if suppose we are given a topological space X, let's consider this space X here, and this space X this was given to be path connected. So this X is path connected. That is, if we have any 2 points here, say this is point x0 and this is point x1, then we have a continuous map from the interval 0 1 to the space X, such that this f of 0 is x0 and this f of 1 is x1. That is what we mean by a path connected space. So there is a path between any 2 points in this space X. Now for this space X, say we have these 2 points x0 and x1 in space X, then fundamental group of X based at this point x0 and the fundamental group of the same space X based at x1. We proved in last lecture that these two groups, they are isomorphic. So then we note that to define the fundamental group of a space X which is given to be path connected, we do not need to mention these base points. So we just write the fundamental group of X as pi 1 of X. Now we are going to prove another result about the simply connected spaces. So suppose we have this space X here, so this space is simply connected. However, if we consider this space here, suppose this space has this hole here, so this space is not simply connected. This is not simply connected. However, this space X, this is here a simply connected space. Now what we are going to prove, so first let us make a definition here. So a path connected topological space X is said to be simply connected if its fundamental group is trivial group. So a path connected space topological space X is said to be simply connected if its fundamental group is a trivial group. That is, this pi 1x, it is given to be equal to the singleton set X which contain the identity element, that is the trivial element, I mean the homotopy class of the constant loop. So this X is in X. So in that case X is said to be simply connected. Now we are going to prove the following proposition. So a topological space X is simply connected. A topological space X is simply connected. So this is the classification of these simply connected spaces, characterization of these simply connected spaces. So a topological space X is simply connected if and only if all paths with fixed endpoints are homotopy. All paths in X with fixed endpoints are homotopic to each other. So let us prove this. We'll first prove this direction, that is, we first consider X to be a simply connected space X, then we prove that any two paths are simply connected. Any two paths in X are homotopic. So let us suppose we have the space X here. So let us suppose there are two paths. This is path F and this is path G. So we can cook up a homotopy H such that which prove that these two maps F and G, they are homotopic to each other. However, if we have a multiple connected space, I mean a space which is not simply connected, say let us suppose this space has hole here. So if we take, that means there must exist two paths such that which are not homotopic to each other. So if we consider this path here and this path here, so these two paths, they cover this hole. Now these two paths are not homotopic because we cannot cook up a homotopy which take this F here to this G here because of this hole. Because if we consider this line segment here, so this point cannot be carried out to this point continuously due to this hole. That means this space is not simply connected. So we are first proving this direction. So first we consider X to be simply connected. Let X be a simply connected space. So that is its fundamental group is trivial, that is pi 1 of X is a trivial group. Now we have to prove any two paths in X are homotopic. So let us consider two paths in X. Let F and G be two paths in X. So these are given to be two paths. So these two paths, they have fixed endpoints. So with F of 0 is equal to G of 0 is equal to, suppose X naught. So this is, let us suppose say X naught, and F of 1 is equal to G of 1 is equal to, suppose this is, suppose X1 here. So this is x1 here, say, huh? So we have a space here which is given to be simply connected, and we have two paths here. This is path, say this is path f here, this is path g, and this is x0 here, and this is x1. And now one can observe that so if we take this product here, f product with g inverse, so first we are traveling f, so we are traveling f, and then we travel g inverse, that means we have to travel g backward. So when we reach here, so from this point x1 we have to travel g back to x0. So this product here is actually a loop based at point x0. So this is a loop based at x0, but it is given that this fundamental group is trivial, but pi 1 of x, so this is trivial group, but pi 1 x being trivial group, we have this homotopy class of f so homotopy class of fg, this will be the homotopy class of, because this contains only one element, that is the homotopy class, I mean the constant homotopy class, that is, say this is x0. So now we know that this pi 1 x, this contains the homotopy classes of all maps, so these two maps must be equal because this is a singleton set. Now these two classes being equal, so it is g inverse here, sorry, so it forces this product f dot g inverse to be homotopic to the constant loop cx. This implies that the product f dot g inverse, this is homotopic to the constant loop cx0. Now let us consider this product. Now let us consider this product here. We take f dot g inverse product with g, so this is homotopic to, now this product here, this is homotopic to cx0, so this is dot g. So this implies because this product here is homotopic to cx0. Now g inverse dot g inverse, so first we have to travel g inverse, then g, so this is a constant loop based at x1. So this implies that f composite with, now this product here, this is cx1, this is homotopic to cx0 product with g, hence, and this product here, this is f, and this product here, this is g, so hence f will be homotopic to g. Now let us prove the another direction here. So now next we are going to prove this direction. So we consider any two paths in X and assume these two paths are homotopic, and we are going to prove pi 1x is trivial, i.e. X is simply connected. So let us consider two paths. Let f and g be two paths in X with fixed endpoints such that f of 0 is same as g of 0 is let us consider these two paths like that, such that so we are going to consider f to be a path from x0 to x1. So this is x0, this is x1, and we are going to take this g to be a loop based at this x0. So this is path g, this is path f. So such that f of 0 is equal to x0, f of 1 is equal to x1, and g of 0 is same as g of 1 is same as x0. Now note that now if we take this product here, g product with f, so first we are traveling g, so we are going from x0 to x0, and then we have to travel f. So from x0 to x0, then x0 to x1, this is a path, this g dot f from x0 to x1. So note that this product is a path from x0 to x1, and so this means since we assume that any two paths with fixed endpoints are homotopic, now f is a path from x0 to x1. So this f is a path from x0 to x1. Similarly, g is a path from this product gf, this is a path from x0 to x1. Now these two paths, that means f and this product gf, these two paths here, they have fixed endpoints x0 and x1. So by the hypothesis, these two paths must be homotopic to each other, and so f and the product this product gf are two paths with same endpoints, are two paths with same endpoints. Therefore these two paths are homotopic. Therefore by hypothesis the path g dot f is homotopic to f. Now this further implies that now let us take these two paths. So if we take a product here by, if we take product on the right side, by F inverse. So this G, since F inverse is homotopic to F inverse, so let us take product of these two, because we know that product of homotopic bus is homotopic. So let us take up this product here. So this is G dot F inverse is homotopic to F dot F inverse, or so this G is G and this F dot F inverse. F dot F inverse is a loop based at so first we are telling F from x0 to x1, then F inverse from x1 back to x0. So this is a loop based at x0. So this implies that, or G is homotopic to the constant loop Gx0. More generally, so if we take the constant, if we take this homotopic class of G, so this is same as the homotopic class Cx0. Now, since the loop G is arbitrary, we conclude that the fundamental group based at of X is trivial group, because G we took G here to be an arbitrary loop. So since the loop G was chosen arbitrarily, so we conclude that this fundamental group X is trivial. Now let us do some examples. So this is example 1. So first example, so we prove this Rn is simply connected. So to prove Rn is simply connected, what we are going to prove? We are going to prove this, the fundamental group of this Rn is the trivial group. So solution to prove, so we shall prove by one of Rn, this is the trivial groups. So this is, suppose, the constant homotopic class Cx0 or Cx, where this X is in Rn. Now to prove this is trivial, it suffices to prove any two paths in Rn with fixed endpoints are homotopic. It suffices to prove that any two paths in Rn with same endpoints, any two paths in Rn with same endpoints, say x0 and x0 and x1 are homotopic. Now let us suppose this is over Rn. Now let us choose two paths, say F and G. This is path F, this is path G. This is x0, this is x1. So let F and G be two paths in X. So these are the continuous maps from interval I to X, such that f of 0 is same as g of 0 is equal to x0, and f of 1 is same as g of 1 is same as x1. So we have already shown that this Rn is in Rn any two paths are homotopy. So we can cook up a homotopy which will prove that these two maps they are homotopy. So one of the homotopies is a linear homotopy. So consider the map, say this map is from, consider the map H from I cross I to X, sorry Rn, this is, sorry I cross I to Rn, given as, defined as this H takes the pair S and T to, so this pair is mapped to 1 minus T times of Fs plus T times Gs. So this is true for all S and T in I. So we have already shown that this is a homotopy. I is a continuous map such that when we restrict H, when we substitute T equal to 0, here we get map F. When we substitute map T is equal to 1, here we get the map G, and this H, these maps the point is say 0T to the point x0 and the line 1T to the point x1. So we have already shown this in previous lectures. So indeed H is a homotopy between F and G, and hence Rn is simply connected. Now let us consider another example. Let us prove that. So this example is left as an home assignment for the viewers. So show that Dn, where this Dn, this consists all those n tuples with real components such that the length of these vectors is either 1 or less than 1. Show that this Dn is simply connected. There is one more example. Show that the set, say X, which is subset of Rn where this X contains all those vectors of Rn whose length is bigger or equal to half but less or equal to 1. Let us 1. So show that this set X is not simply connected. Is not simply connected. So we have to exhibit two paths in this X, and so this is an easy exercise. So this is this annular region. So this is this region here. So we have to exhibit two paths in this case. Say this is path F and this is path G. So we have to exhibit these two paths and show that these two paths are not homotopic. Obviously these two paths are not homotopic because we cannot take this point, say this is point S. So there is no homotopy, there is no continuous family of maps which takes this point here to the point here. Say this is point F of G of S. There is no such homotopy here. So we have to show that this annular region is not simply connected.